This is Bill Farmer again. Welcome back to Software Engineering 2FA3, Discrete Mathematics and Applications 2. Today we're going to be talking about various kinds of grammars. Some of these are going to be context-free grammars and others are going to be non-context-free grammars. So we're going to begin to talk about ways you can take a context-free grammar and simplify it. So we're going to need to make some definitions. The first is we can define a non-terminal, A, to be useful if there's some derivation that actually uses that non-terminal. So if there's no way to have a derivation that uses a non-terminal, we'll say that non-terminal is not useful, it's useless. So useless non-terminals really, they provide no benefit to us at all. The second thing is we're going to say an epsilon production is a production of this form. It's a production that just produces the empty string. And a unit production is a production of this form. It takes one non-terminal to another non-terminal. And it's pretty easy to prove a theorem which says every context-free language that does not contain epsilon is generated by some context-free grammar that has no useless non-terminals, no e-productions, or unit productions. So in other words, we can eliminate all three of these things for any language as long as that language does not contain the empty string. Now, the main developer of many of these ideas was Noam Chomsky, and there's a normal form named after him called the Chomsky normal form. We'll say a grammar is in the Chomsky normal form if all its productions either look like this: a terminal goes to a pair of terminals, or a terminal goes to a non-terminal. And there's a theorem that you can see how it's proven, Lecture 21 in Dexter Cozen's book, Automata and Computability. The theorem says that every context-free language not containing the empty string is generated by some context-free grammar in Chomsky normal form. So if we have a context-free language that's not including epsilon, we can assume that there's a grammar that has productions of old in this form. Okay, so here's an example. Here's a context-free grammar that we gave in exercise 5. It has these productions. Notice that this is certainly not in Chomsky normal form. Notice it does not generate the empty string, but we can easily find an equivalence grammar in context normal form. So I'm going to show how to do that. I'm just going to modify this grammar a bit. So I'm going to have S go to, instead of A, I'm going to have it go to something I would just call X sub A, B, and B will go to X sub B, A. So this non-terminal goes to a pair of non-terminals. That's good. And I'm going to have A goes to X sub B. And I'm going to have AA, instead of AA here, I'm going to replace that with YA. And this will go to X sub A S, and that goes to A. All of those had the right form for Chomsky normal form. Similarly for B. This is B. And now all I have to do is say what XA goes to. It goes to A. What does XB go to? It goes to B. What does YA go to? It goes to AA, and YB goes to BB. So this is a new set of productions. We have a new grammar, but it's pretty obvious this grammar and the previous grammar are equivalent. They both generate the same language. Okay, there's another kind of form. It's called the Greibach normal form. This was introduced by Sheila Greibach. I don't remember the exact year when she did this work, but I think it was in the 1960s. All the productions have this form. They start with a non-terminal, and they have any number of, they start with a terminal, and they have any number of non-terminals following that, where any number includes having no non-terminals at all. So this is, if all your productions are in this form, you would say your grammar is in Greibach normal form. Now, every context-free language not containing epsilon is generated by some grammar in Greibach normal form. If you want to see the proof of this, you can see Lecture 21 in Cozen's book, Automata and Computability. Now, let's look at some other ways of other special grammars. One kind is a grammar that's linear. It's linear if all its productions have at most one occurrence of a non-terminal on the right-hand side. That means it goes to something like this. A1 up to AM, B, B1 up to Bn. So it's a string of non-terminals, but there can be at most one, it's a string of terminals with at most one non-terminal. Of course, we could also have something like this. It has no non-terminals at all. Okay, so that is a grammar that's linear, and we'll say a language is linear if it's generated by some linear context-free grammar. And a context-free grammar is right linear, so it's a special kind of linear, where all the productions look like this or this. That would be right linear. And it's left linear if they all look like this or this. And we'll say a context-free grammar is regular if it is either right linear or left linear. And there's a theorem: a language is regular if and only if it is generated by a regular context-free grammar. So I promised you a while back that another way of characterizing languages is with context-free grammars. A language is regular if it has a context-free grammar that's either right linear or left linear. And another theorem is there are linear languages that are not regular. And we had some examples. We had the example of palindromes. Palindromes are context-free, and they're, well, actually, let's just go back and look at that. We had this example of palindromes, and palindromes are context-free but not regular, but you see they are linear because I only have one occurrence of my non-terminals on the right. And another example was this language A to the N, B to the N. This language is also context-free but not regular. And notice again, it's a linear language because it has a grammar whose productions are all linear. Okay, so those are some important special cases of context-free grammars, linear and regular grammars. The next thing we want to look at is the pumping lemma for context-free languages. So I mentioned earlier there was a pumping lemma for regular languages that says that every sufficiently long string in a regular language contains a short substring that can be pumped. That means we can take this string and repeat it as many times as we want, and that new string we get by repeating the substring will still be a member of our language. We didn't really look at this lemma too much, but this lemma is useful for showing that languages are not regular. So we're going to now look in some detail at the pumping lemma for context-free languages, which says that every sufficiently long string in a context-free language can be divided in 5 segments, such that the middle 3 segments are short, but the second and fourth can be simultaneously pumped. And so I'm going to explain what that is. This lemma is lemma 5. It's a pumping lemma for context-free grammars. So let L here be any context-free language. Then L will have a constant I'll call n sub L. So every context-free language will have this constant. And what's important is if we have a string in L, Z, whose length is greater than or equal to the length of this constant. In other words, it's a long string, long with respect to this constant. Then it's going to have 5 parts: U, V, W, X, and Y. Where the length of V and X are greater or equal to 1. And all that says is V and X are not both empty. And the length of VWX, the middle part, is short in the sense it's less than or equal to the length, less than or equal to this constant n sub L. And for all I greater than or equal to 0, I can look at this string where I repeat the V portion I times, I repeat the X portion I times, and the string I get is still an L. So this is what it means to pump this string, is I can increase at the same time V and X, adding more copies of V and X, and I will stay in this language. So you can go to Cozen's book, 100 pages 150 to 53 of his book Automata and Computing, and you can see a proof of this. So let me explain this again. If we have a context-free language, we're going to have one of these constants. And if we take a string that's bigger than this, has a length bigger than this constant, greater than this constant, then the string will be broken into 3 parts, and it will satisfy these 3 properties. And the third property is the interesting property because it basically says we can pump this string. Okay, so I'm going to show you an example how we can use the pumping lemma to show that a language is not context-free. So here's my language. It's the set of all strings of A, N, B, N, C of N. All strings of this form, and where we have a string of A, string of B's, and a string of C's, but the length of each of these substrings is N. And N can be any number greater than or equal to 0. So the claim is that this language is not context-free. And we're going to use the pumping lemma to show it. So let's suppose the language is context-free. So we're going to make this assumption. And by the pumping lemma, we know that there's going to be this constant. We don't know how big it is. Or we'd have to look at the proof of the pumping lemma to get some idea how big this is. But we know it exists. And so let Z be this string. A to the n sub L, B to the n sub L, C to the n sub L. And so this string is clearly greater than our constant. In fact, it's 3 times the length of the constant. And so that means Z breaks into 3 parts. And these 3 parts satisfy the 3 properties. These 3 properties up here of our lemma. And in particular, the second property says that the middle parts are going to be less than or equal to the length n. Now this is crucial. These middle part, so let me write it like this. This middle part is less than or equal to length n. And we know that the whole length is of length 3 to the n. So that means that if our string is broken that part and it has B's and A's, let's say a bunch of A's, a bunch of B's, and a bunch of C's, this part here, it has to be contained in this part, or it has to be contained in this part. It's too short to be contained in the part of A's, B's, and C's. It's either is a string of A's and B's or a string of B's and C's. It can't be of all three. So then, if it's contained in here, when we pump the string, this string Z, that means we can increase A's and B's, but we won't be able to increase C's. And this is a contradiction to the structure of L, because if we can increase the number of A's and B's but not C's, we're producing a string that's not a member of this. So by the pumping lemma, we know that L cannot be context-free. Okay, so let's look at another kind of grammar. This is what's called a context-sensitive grammar. It's just like a context-free grammar, but we have a more general kind of set of productions. So remember, with a context-free grammar, our productions always look like this. It's always a non-terminal goes to some string of non-terminals and terminals. So here, we can have productions of this form where we have some string, a non-terminal, some string, and that goes to the same string alpha, gamma, same string beta. So we change A in the context of alpha and beta to alpha, gamma, beta. And alpha and beta can be any strings of non-terminals and terminals. Gamma must be a non-empty string. So we're allowing more productions, but we are making sure that A can go to any string in the context of alpha and beta. It can go to any string, but that string must be non-empty. So we call these context-sensitive grammars. And if we really want to get epsilon somehow, we can just add the production S goes to epsilon. That still is fine for a context-sensitive grammar. But we can't use S then on the right-hand side of any productions. That would violate our situation here. Now, the thing to notice is that the length of this, the left-hand side, is always less or equal to the length of the right-hand side. That's true for context-free grammars. It's also true for context-sensitive grammars. So a language is context-sensitive if it is generated by some context-sensitive grammar. The reason it's called context-sensitive is because our productions can be context-sensitive. They can depend on replacing a non-terminal, can depend on the context of where it is. And we have an example of a context-sensitive language. That's this language A to the N, B to the N, C to the N. Just a moment ago, we showed that this language is not context-free, and I'm making the claim it is context-sensitive. Okay, we have one more kind of grammar to look at. This is called a general grammar. It's like a context-free grammar, a context-sensitive grammar, except the productions here are completely general. We can go from any string of non-terminals and terminals to any string of non-terminals and non-terminals. So productions are completely unrestricted, and in particular, beta could have length less than alpha. So this is not the case for context-sensitive or context-free grammars. In those grammars, the right-hand side of your production is always bigger than or equal to the length of the left-hand side. But here, productions can make things bigger, also makes things smaller. And there's a theorem that says that any language generated by a general grammar, that language, a language that can be generated by a general grammar is going to be recursively enumerable, and a recursively enumerable language can be always generated by some general grammar. Recursively enumerable means that we can write a computer program that will enumerate the language. That means we start running the program and it can print a member of the language, and then it will print another member of the language, and it will print another member of the language, and it will keep going, and every member of the language will eventually be printed. That's what print recursively enumerable means. Okay, so this completes the grammar part of this topic. Next time we're going to start talking about the automata part of it. We're going to talk about a new kind of automaton, push-down automata. And that's what we'll do next time. See you then.